Hi everyone, I'm Thomas. Thank you all for coming. I'm presenting this work in collaboration with Shivam Nadimpalli and Yuen, and I'm here to talk to you about testing and learning quantum Juntas nearly optimally. So let me start up by setting up the main topic of the study, so a quantum junta. So a junta is a function that acts on a small number of its inputs, and we define a quantum junta similarly as a unitary that will act non-trivially on only some of its qubits, so k out of the n. For the purpose of this talk, k will be a constant, and n will be something that's very large. And the form that we write the unitary as is V tensor I, where V is a unitary that acts on k qubits, and n is the ambient dimension. So you can see that such a unitary will take like this recurrent structure here. And briefly, let's talk about like the motivation of like why these objects are interesting. So in nature, you can imagine that there are some processes that will act only on some of its qubits, and someone may be interested in doing like one of two things. One, to determine whether something is a junta, and two, if they know something is a junta, then perhaps you can do tomography on it, like learn a classical description of it in fewer queries than if you didn't know if it was a junta. So especially since the classical or normal tomography takes exponential in the ambient dimension number of queries, this can potentially be helpful if you do know actually it only depends on some number of its inputs. So I laid out two questions there, one about testing, one about learning. So let me just first lay out what the framework is of property testing. So this is how we're going to set up this problem. So on the left is like a more like decision version where you're trying to, it's like, instead of like asking if something is a k-junta or not a k-junta, we're actually going to relax the question a little bit in the framework of property testing, where we want to find an algorithm that can tell if a unitary given access is a k-junta or if it's far from a k-junta. And if you can do these two things, then that's what we're looking for. And more formally, here's the question that we're going to tackle. So we're given query access to this unitary U, and we want an algorithm that when the unitary is a k-junta, so it depends on only k of its qubits, then it'll tell us that it's a k-junta. And on the other hand, if the unitary is far from a k-junta by some distance metric, which we'll define later, then we want the algorithm to tell us that it indeed is far from a junta. So that's the setup of the question in property testing. And let me first give you some prior results that's been done. And so the important similar result that's been done is in testing and learning Boolean functions. So given access to a Boolean function, you can develop a quantum algorithm to do testing. And this actually, in a very nice paper, was shown to take square root k queries by Mbanis et al. And there's a matching lower bound for square root k queries here. So it's a very interesting result. Square root k is perhaps different from what you would expect with k. And for the learning side, you can also develop a quantum learning algorithm that will learn such k-juntas into the k queries. So here we're not dealing with testing or learning classical functions, Boolean functions. We're working with quantum juntas, which are unitaries. And in doing so, like the bottom table will show like the results that we're going to demonstrate. So in particular, we're going to follow up on Wang's work in 2011, on which pioneered testing quantum juntas, and we're going to show that to test a quantum junta with a quantum algorithm, you need square root k queries, and to learn it, you need 4 to the k queries. So this is the contribution of this work. Okay. So let me get into some preliminaries, and then we can talk about the main results. So the distance metric I mentioned before that we're going to use to define farness, so farness from a k-junta, is essentially the distance induced by the Hilbert-Schmidt norm. There is some subtlety in the paper that we use, but for the purpose of this talk, we can just omit those. And we define distance essentially by like taking the norm of the subtracted matrices. And the second primitive we'll need is the Choi-Jamakowski S-morphism. So this is a really useful correspondence between a unitary and a state. And we can utilize this correspondence in our algorithms, which you'll see shortly. Okay, so I'm going to talk about the two sets of results. So one on testing, one on learning. And here's to start off the testing result. So essentially, we show that there's an algorithm that takes close to square root k queries to do testing. So to test if a unitary is a k-Junta or far from k-Junta. And furthermore, we also show a lower bound for this. So it takes at least square root k queries in order to do this problem. So let me start off by giving you an overview of the algorithm and the techniques. So testing classical Boolean functions for being a Junta, there are techniques that are used like Fourier analysis. So here we're going to use like a form of quantum Fourier analysis. And in particular, we're going to define a notion of influence of a qubit. So how important is a qubit for how non-trivially does it act on that qubit? And then we're going to create an algorithm that will estimate this influence. So given a subset of qubits, can you estimate what the influence is of this set? And then finally, we'll combine the influence tester, so the algorithm that estimates the influence. And then we're going to combine this using with the technique pioneered by Ambanis in 2016, Ambanis et al. In 2016. And this will give us a quantum Junta tester. So I'll elucidate that connection toward the end of this section. So let me start off by defining a notion of influence. So I should say from the start that this notion was pioneered by Montanaro and Osborne for quantum Boolean functions. So let me start off by recalling that a n-qubit unitary matrix can be decomposed in the fashion you see above. So essentially, you can think of this as a sort of Fourier decomposition. So you have 4 to the n terms, and each term is corresponding to one of these sigma x matrices. So each of these matrices, sigma x, corresponds to a tensor product of Pauli matrices, and associated with each sigma x is a complex coefficient. So this is a Fourier coefficient, if you will. And the way we define influence here is we add up the square norms of the coefficients that correspond to sigma x's that act non-trivially on qubit j. So we can extend this definition for a subset of qubits, but instead of going to the details, let me just talk about like why this notion of influence is natural and what it tries to capture. So in the form of the definition we saw before, what this influence is trying to capture is how non-trivially a unitary acts on qubit j. So we're adding up the terms that correspond to those sigma x's. And the reason this is natural is that it has a lot of interesting properties that are analogous to Boolean functions. So in particular, the Boolean analog of this is for a Boolean function, you can define the influence in this following way. And it has, the form of this influence is like very similar. And in particular, there's a lot of nice properties that follow from this notion of influence. So the monotonicity is a property that we'll need in the proof in addition to subadditivity. And there's also this really interesting property that was proved by Wang in 2011. And essentially, it's like a very analogous result to what you have in the Boolean case, where essentially the complement of every set of k qubits will have some non-negligible amount of influence. Okay, so with that said, we've defined the notion of influence. So let me talk about an algorithm that will estimate this influence. And then from there, I'll talk about the connection to Junta testing. So what this algorithm is trying to do is that it takes a subset S of the n qubits, and it's going to output a number 0 to 1. 0 or 1, and the probability with which it outputs 1 is going to equal the influence. So essentially, in this sense, this algorithm will estimate the influence, and if you can run this multiple times or use amplitude amplification, then you have something that will like estimate the influence for you. So what this algorithm does is that it prepares this Choi-Jamakowski state for the unitary, and then it will measure some subset of the qubits. And you can show that the probability of the outcomes of this measurement correspond to the influence. So let me just illustrate this for you. So first, we're going to prepare the Choi-Jamakowski isomorphism. So that's done by taking n EPR pairs, and then we're going to apply the unitary on just say like the left half of it. Okay, and then let's say we want our subset of qubits, we want to estimate the influences is 1 and 2. Then we'll measure these 4 qubits. And then the measurement outcome will be distributed in such a way that if you output 1 for one of the outcomes, then you'll get exactly the condition that you would like, where the expected value is equal to the influence of the subset of qubits. So in this sense, we now have an influence tester. And why is this important? Well, it allows us to get this key lemma here, where essentially we feed in a subset of qubits, and we can determine with a small number of queries whether the influence is above a certain threshold. So the way the connection of this with Hunter testing is through this problem called group testing. So I'll explain briefly what group testing is, and then I'll talk about the connection to Hunter testing. So in 2016, there was this amazing result where given access to this intersex oracle, so this intersex oracle has an unknown set A of n, and it will output 1 if the input set has a non-zero intersection with this mystery set, and otherwise it will output 0. So given access to this intersex oracle, the problem of group testing is whether you can decide how large the set A is. And it turns out you can do this with a smaller number of queries using quantum algorithms. And if you combine this with the influence tester, then you get a small number, or a Hunter tester with a small number of queries. And to talk about the connection or how we use group testing for this, let me talk on a high level about the main question you need to answer when you're testing if something is a Hunter or far from Hunter. And namely, if something is far from a Hunter, then you can sort of pick that out, glean that information by looking at the distribution of the influence. So in short, in the techniques, there's roughly two cases. So one is where the influence is distributed in such a way where there's a lot of influence and a small number of qubits. So that's what you see here. And then the second case is the case where the influence is more spread out. So the influence is distributed something that looks like this. And in the first case, this is a case where roughly if you're trying to detect a distribution of influence in this that follows this form, then roughly you'll find that the influence tester, so testing of a subset of qubits, has an influence above a certain threshold. This is roughly like asking, does the subset of qubits you have one of the really high influence qubits? So with this connection, you can see that in this case, the influence tester behaves sort of like an intersex oracle on a high level. And therefore, we can use group testing to sort of suss out this case. So that's how we detect if something is far from a Hunter in this case. And then the second case is when it's more evenly distributed. In this case, the technique is that you will pick a random subset of the qubits and then measure the influence of that random subset. So if the influence is more spread out like this, then on average, or rather with very high chance, the random subset of qubits you pick out will have a large influence. And this is something you can suss out with an influence tester. So we talked about the techniques to detect if something is far from a Hunter. Essentially, that gives us an algorithm that will test if a unitary is a Hunter or far from a Hunter in square root k queries. And now I'll talk about the lower bound. So we want to show that this takes at least square root k queries, and there's a very natural result to reduce from. So in particular, testing if a Boolean function is a k-Hunter or far from a Hunter takes square root k queries. And we reduce from this by encoding a Boolean function along the diagonal of a unitary matrix. So we're going to given a Boolean function f, we'll encode it in this following way. And what we would like to show is this key lemma here. So if f is far from a k-Hunter, a Boolean k-Hunter, then we would like to show that uf is also far from every quantum k-Hunter. So the key structural result you need to show this is up here. And instead of talking about the details, let me just illustrate it for you. So let's suppose that f is far from every Boolean k-Hunter. Then you can show pretty easily that the encoding uf will be some distance away from the set of encodings ug. So g is a Boolean k-Hunter. So there will be some gap here. And the key part of the structural result is to show that for every quantum k-Hunter, that it's close to some member of the set ug. So if there's some constraint here, but these two must be very far away, then this implies like a gap between UF and V. And that is essentially the structural result. Okay, so we've talked about the upper and lower bound. Now let me just briefly talk about the other set of results around learning. So we're given the query access to U, and we want to output a classical description, and this can be done in 4K queries. So the approach here is very similar to the algorithm by Atichi Sredio in '07, and let me just roughly lay it out, and we'll save the details for the Q&A if there's time. So the idea is that you don't know what the qubits are that have influence. So what you do is you use this subroutine called Pauli sampling, and from there you can determine what the qubits are that have a non-negligible amount of influence. Once you know these qubits, then you can produce a state, a Choi-Jankowski state, on these important qubits. And such a state on the important qubits will be small, so it'll have like no more than 2K qubits. And furthermore, it'll also be a pretty faithful representation of the actual unitary U, because it essentially holds all the qubits that have non-negligible influence. So once we have such a state, then we can produce many copies, and we can learn this with tomography. And in this way, we can output a classical description of the important part of the junta. These are some more details, but let's save that for later if anyone's interested. And the one subroutine I do want to highlight here is that of Pauli sampling. So what is the subroutine that can allow us to figure out what the important qubits are? And this subroutine is like very similar to the influence estimator. Essentially, we're going to repeat the same procedure some number of times, and the procedure we repeat is we're going to prepare the state corresponding to U, and then we're going to measure it in the Pauli basis. So the Pauli basis is like the set of Choi-Jankowski states corresponding to these sigma x's, and why this, or intuitively why this works is that like if a qubit is important, then like it'll have like some set of coefficients that are large, and then it'll show up in the measurement. Okay, so these are some details, but let me just briefly talk about the lower bound. So we talked about an algorithm that will learn a quantum junta in 4K queries. So we need to show now a matching lower bound. The way we do this is with communication complexity. So in particular, we have this input guessing game that we reduce from. And in this game, Alice is given a random input. And Bob has to communicate with Alice quantumly. And after communicating with Alice, output a guess for what that input is. So essentially the high-level overview of this reduction is that one way that Bob can figure out like what input Alice has is to simulate like learning algorithm. So whenever like the algorithm queries a quantum state psi, then Alice will return U times psi. Okay, so those are the results. So 4 to the k for learning, square root k for testing, and just to sum up, so we've defined a notion of influence. We've looked at the complexity of testing quantum juntas and learning quantum juntas, and tying this back to the original motivation. So if we have like an unknown process, then we're now able to test it in a small number of queries, and also we can, if we know it's a junta, then we can learn it in a much smaller number of queries than if we just did naive tomography. Okay, so here are some future directions, but I think I'll open it up to questions right now. No?
I'm sure there are some questions. And you could also mention maybe your favorite future direction since, well, we're getting the question set up.
Sure. Yeah, I mean, these are some ideas we were looking at before this work. So there's like been some work in tolerant property testing, which is sort of like instead of telling if something is a k-junta or far from a k-junta, you're trying to tell if something is like delta close to a k-junta or epsilon far from k-junta. And this problem seemed interesting because there was some recent work in 2021. And also there was like an interesting talk yesterday about like, so this work deals with a lot about like Boolean analysis and generalization to quantum. So there was a really interesting talk yesterday about like the quantum analog of like the KKL theorem, and there might be like some interesting directions there where you try to like generalize results from, or like more results from the Boolean case. Yeah.
So your results follow the structure of the Boolean results, which means that they are very tied to this like qubit tensor structure which is behind. Did you think about extensions, whether there is some like 2 to the k subdimension where it is non-trivial and then the rest it's trivial? Because in the unitary case, that's a generalization that you can do, which is obviously not possible in the Boolean case.
I'm sorry. So you're asking if there's like so in this generalization of unitary matrices, is there like a particular set of unitary matrices that are difficult to test?
So that it's rather than asking whether there is k qubits such that the unitary is non-trivial on these k qubits and otherwise trivial, asking whether there is a 2 to the k dimensional subspace where it's non-trivial and tensor with identity on the rest.
I see. Yeah, I think we actually looked at a similar question to this. I don't know if it's exactly what you're talking about. Yeah, we weren't able to make any progress on it. It was like not clear to like how to define like the general form of such a matrix. But I think it is an interesting question. So thank you. Yeah.
Okay. Thank you for the interesting talk. I have a question about the lower bound in the testing case that you showed. So you proved that by basically embedding the classical problem, if I understood that right?
Yeah, that's right.
One conceptual question that I have is the classical lower bound against classical queries or also against quantum superposition queries? Because in principle here you could query the unitary in superposition, right?
Yeah. So like you query the unitary on a arbitrary quantum state, and the classical result is for like a quantum algorithm. So a quantum algorithm takes at least square k queries. Yeah.
Okay. Thanks.
Thanks for the talk. I have a question about the testing the k-Juntas. From my understanding, you consider a situation where you have access to the U and U dagger, right?
Yeah.
And I'm wondering if you only have access to the U itself. Can you prove some lower bound, upper bound in that situation?
Oh, so you're asking about like the lower bound and upper bound for the case when you only have U?
Yeah, only U.
Only U. Yeah, I'm not. So like the reason we need U dagger here is because of amplitude amplification. So probably if you don't have U dagger, then it might be hard to get the square k upper bound. So maybe like you see everything like shifted up a little.
Okay.
But yeah, we haven't looked into that.
Okay.
Yeah, perhaps that's like an open question.
Okay. Thank you.
Thank you.
There would be time for one more question, if someone has a quick one.
So I was wondering whether so it seems like you're actually able to test for something that's slightly more general than Juntas. Like you can test whether most of the influence is concentrated in like a few coordinates or a few qubits. Have you thought about sort of extending in that direction, or is the testing problem there become sort of like trivial?
Oh, so you're talking about like the techniques for the upper bound? Like,
yeah.
Sort of here. Yeah. Yeah. This is like a very very creative approach. I haven't looked into like how else you might use it. Perhaps you could use it for like, yeah, I mean, here like we sort of cover like a very general set of distributions of the influence. I'm not sure, there's like no question that comes immediately to mind, but maybe you can like use this technique in another way. Yeah, was there something you had in mind?
Because it seemed, at least naively to me, that like you could just use the same algorithm to test for something that's slightly more general. I was just wondering if that was the case, or if there's, so perhaps like if you consider, say, like the set of all functions that have influence mostly concentrated on k qubits, then that's like too large a class of functions, so the testing problem doesn't really make much sense. But if not, then it seems like this same algorithm could work in that case.
Yeah, I mean, where like the influence is like concentrated in like, let's say like 2k qubits, but there's like still some residual influence. Yeah. I mean, that's like essentially like the case that this is dealing with. Like when you have like a function that's epsilon far from k-Junta, then like it'll have like, it can possibly have some influence in like a very large number of qubits, but it's just like the influence in those qubits is like very small. So this sort of like does deal with that case. Yeah.
Okay, thanks.
All right, so let's thank Thomas again for the nice talk and all the speakers of the session.